Cool. I'm just going to say a few words then, just in case there's anyone here for the first time or watching afterwards. So for those of you that don't know me, my name is Barry Cranford. I'm the founder of the London Java community. So I'm not a developer myself. I run a tech recruitment company called RecWorks. So here at RecWorks, we've been on a mission for the last 12 years now to prove that recruitment can be a force for good in the tech industry beyond just getting people jobs. And that's specifically around learning, mentoring, and career development, that kind of thing. So put simply, if people want to learn and people are happy to teach or to share, then we want to bring people together. And that can be on a group basis, like this evening, or more on a one-to-one level. So one of the biggest examples of what we do is our Meet a Mentor community, which has got really close links with the LJC. So we organize introductions between mentors and mentees at all levels. And this is what, if possible, we could do some help with. So we've got people, students, mid-level engineers, seniors that are signing up all the time. And so anyone out there that wants to get involved in some mentoring, then please do come forward. So there's other things as well within the Meet a Mentor community. One of those is this aspiring speakers group, which is where we've got Zam and Lakshmi speaking this evening. So the aspiring speakers group is just a collection of people that are looking to get into and step up onto the conference speaking circuit. So again, if there's anybody that would like to join, we do a bunch of things, Zoom calls, Q&As. There's a monthly workshop and that kind of thing, obviously an opportunity to speak. And that is what tonight's all about. So Lakshmi and Zam, they've both given a couple of lightning talks to us, and this is their first full talks. So without further ado, I'm going to hand over to Zam, who's going to be speaking on becoming a hash map connoisseur. So good luck.
Thank you. All right. Just going to share my screen. Okay, fantastic. Can everyone see my screen? That's a yes.
I can see it.
Oh, great. Okay, cool. So today I want to talk about becoming a hash map connoisseur. So a little about myself. My name is Zam. I work as a software developer on backend systems at a company called Transfic. We build normalized APIs for companies looking to trade on fixed income markets. So a little overview of what we're going to be talking about today. First of all, we're going to be going through a couple of implementations of hash maps. So we're going to go through separate chaining and linear probing very briefly. The idea is that will give you a solid grounding to compare and contrast some of the trade-offs that we will be discussing subsequently. So to start with, a little proviso. Every time I say the word optimization, you should really be thinking in your head of the word trade-off. Really, there is no such thing as a free lunch, and some of these optimizations will really have a negative effect in some other area. But the key to using them efficiently is that if you understand your specific use case, you can decide whether those negative sides even affect your particular use case. So I challenge you to think about all the different trade-offs in all of the different areas I discussed today. So let's take a look at separate chaining. So this is the type of hash map that is, well, it's the implementation that the Java standard library uses for its hash map. And the way it is structured is that we have an array, and the array is of type node, and each node object has a reference to a key, a value, and a next pointer. This is so that you can link various nodes together in a linked list using the next pointer, as I'll demonstrate in a moment. So let's say we want to insert a key. In this case, the key is a string, and the key is James. So the way we would determine how to insert James into the map is that we take the hash code of James. We then modulo that hash code by the length of the array. And in this case, that's 64 modulo by 8. And that results in a 0, which means that James needs to go in the 0th slot in the array. So the way we insert him and his value is that we create a new node, and we put in the key and value into the node object, there's James and the value associated with James, and we leave the next pointer null and slot that into position 0, like so. Now, if we want to insert a second key, then in this case, the key Kate, then we do the same thing. We take the hash code of Kate, we modulo by the length of the array, and we get a 2. That's 74 modulo 8 gives 2. So same thing again, we create a new node object, we sub in the key and value into the node, and then we slot that into position 2 over here. Great. Now, the interesting scenario comes when we actually get our first hash collision. Now, hash collisions occur when we have two keys that will be inserted into the same slot. Now, note that doesn't mean they have the same hash code. It just means that when you take their hash codes and you modulo by the array, you end up with the same number. So in this case, if we want to insert the key Rich, even though Rich has a different hash code to James, once moduloed by the size of the array, we end up at slot 0. So again, we create a node object, and we insert the key and value for Rich into the node, and we use the next pointer on James to create a linked list. And likewise, if we want to insert a third key, which in this case is going to be Jen, who should be at slot 0, we just append to that linked list by doing the same operation. Now, again, none of these keys have to share the same hash code. It's merely the fact that when you modulo those hash codes by the size of the array, do we get the slot? And if we want to do a search for any of these items, it's the same kind of procedure for an insert, except we start it when we iterate through the linked list, we just look for the particular key we're trying to get. Now, if we take a look at a linear probing implementation of a map, you'll see this is already a little bit different in that we actually keep two arrays. The top array is going to be used for the keys. So instead of being of type node, it is actually going to be of type whatever your key is. So if it's a string, then it'll be a string array. And the second array is going to be an array of the type of the value we want to insert. So if we, again, want to insert our first key, James, we do the same calculation. We take the hash code, modulo it by the length of the array, and again, we should arrive at slot 0. Now, there is nothing in slot 0, so it's pretty straightforward. We insert the key into the keys array, and we insert the value into the exact same slot in the values array. So in that way, if we know the position that the key is going to be in, then we can actually find where the value is located when we do a lookup. And again, if we insert Kate into this data structure, same deal, we insert Kate in at slot 2, which is the slot that would arise if you did the hash code modulo by the size of the array again, and that's hunky-dory. The real interesting part is what we do in the situation where there's a collision. Since we don't have node objects, we can't really create linked lists at every slot in this array. So what we instead do is, if we have a hash collision at a particular slot that we're trying to insert at, in this case, Rich is going to try and be inserted at slot 0, but it is occupied by James. So the strategy we employ is that we simply iterate to the right to find the next available empty slot and insert our key there. So if we insert Rich, Rich goes here. Now, interestingly, when we insert the next key, which is Jen, which should go at slot 0, we repeat the process. So we want to insert Jen, but slot 0 is preoccupied. So we iterate to the right, and slot 1 is already occupied by Rich. So we iterate to the right again, and the slot number 2 is occupied by Kate. So we iterate to the right again, and we end up with Jen being here. Now, interesting to note that actually the overflow from all the hash collisions can be intermixed along the array. And that is a key feature of linear probing. So let's take a look at some of the trade-offs that are available to us in maps and examine them in light of these two implementations. So firstly, we're going to take a look at how the memory footprint differs between these two implementations. Now, in the case of the separate chaining map, we have the memory footprint of the array. And in addition, we also have to allocate new node objects every time we want to insert an item into the array. And also when we remove, we will need to we'll null out those particular positions or unlink them from the linked list, in which case we will have those nodes garbage collected. So the memory should grow and reduce with the size with the number of items in the array. And obviously, if we have to resize, then we'll have to get a larger array. Interestingly, you can offset the garbage that's associated with the nodes if you pool those nodes, but that's an optimization that you may or may not want to make depending on your use case. In the case of the linear probing map, we don't have to worry about the nodes. We do have two arrays, so we have a double-sized memory footprint, but we won't actually have to add any extra, well, we don't have to allocate anything as we're adding items to here, unless we have to resize the backing array. So again, this is just illustrates how it's a game of trade-offs as to how you want your memory profile to look. Now, if we move into a discussion of collisions, this is an interesting topic since in an ideal scenario, we would not have any collisions happening. And what I mean by a collision is, as described earlier, if two keys need to be inserted into the same slot, then that usually results in having to do some kind of iteration. In the case of the separate chaining, it's iterating through the linked list at every slot. And in the case of linear probing, it's iterating through the array. But ideally, we'd like to avoid any iteration. In an ideal scenario, every key would have a unique hash code, and that unique hash code would yield you a unique slot in the array when you modulo by the array. And in that scenario, we wouldn't have to do any iteration, and we can achieve that through computer science dream of being able to have an O1 lookup in a map. But this may sound like a bit of a pipe dream, but it is actually feasible in some map implementations. And I'm going to take a little sidetrack to show you an implementation of a basic map that could actually achieve perfect hashing, and that is if the key is an enum. So if the key is an enum, then what we have is we have a known size of set of values. So for the enum color, we know that there's only 3 values that it can possibly be, and each of those values has an associated ordinal that's internally set up by the runtime. And in this case, we could simply create an array that is the same size as the total enum set. And at that point, if we want to do a lookup in it, we could simply use the ordinal of the key to identify the slot in the array. So in this case, we have we have no collisions whatsoever, which is fantastic. But unfortunately, unless you have a type that is small enough that you can actually fit into those kind of data structures, it's very difficult to get that. If your key is a byte, that's another one where it's also feasible, since you only have 255 possible values in there. So, but since we can't discuss perfect hash functions, we should probably try and avoid bad hash functions, since if we have a bad hash function, we're going to end up with more iterations within our various within our two implementations of the map structure. So let's take a look at bad hash codes. So a lot of people think bad hash codes are pretty academic, and no one really writes that like complicated enough hash codes for it to be bad. But here's an example from the Java 1.1 standard library of the hash code for string. Now, if you look at this very briefly, you'll see that if any string that's larger than length 16 has an optimization to avoid having to include every character from the backing character array of a string in the hash code, the code actually took every 8th character from a string, which seems like a very nice optimization to to avoid having to visit every single character and do calculation on it for long strings. But this was very quickly removed soon after, when it was discovered that it actually has a slight problem in that if you have a bunch of strings that share a very long prefix, then you actually have a higher likelihood of ending up with hash collisions, as you can see in this particular case, where we have, if we were to insert these 6 keys, even if we created an array backing structure that was incredibly large, we would still end up with 2 pairs of hash collisions in that array. So it's important to make to think about your hash code implementation. And in fact, if you look at the Java standard library, when it calls hash code on any key that you're trying to insert or get, it will actually double hash the hash code that's returned. So it will take the hash code and it will do a series like an XOR operation of the first 16 bits of the number that gets returned by the second 16 bits, just to rehash it and guard against the potential problems in the hash code. So let's move on to the next point, which is load factor. So a little bit about load factor. Load factor is a value that you can pass into the constructors of numerous hash maps, and it will determine at what point you resize the backing array. And what I mean by that is, in this example over here, let's say we have a separate chaining map, and we have a load factor of 0.75, which is typically the magic number that's used for separate chaining maps. If we have a load factor of 0.75, which is the default one in the Java standard library hash map, then we take the size of the array and we multiply that by the load factor, and that tells us at what threshold beyond which we should resize the backing array. So in this particular case, if we have 4 items in here and we have an 8 size array, then we're going to resize once we get past 6 items. And in the case of a linear probing map, we actually typically use a smaller load factor. The magic number tends to be around 0.5, 0.55 for linear probing maps. So they will resize typically at a smaller threshold. And the reason behind that is that, unlike with separate chaining, where we store the overflow of hash collisions in a linked list that is at that particular slot, because we are storing the overflow of hash collisions inside the same array, we can get a certain behavior called clustering, which you are seeing in this particular implementation, where you'll get a bunch of slots occupied just because slot 0 overflowed by a couple. And if you say want to insert a key at slot 1 over here, even though we've not inserted any key directly in slot 1, we've inserted keys at slot 0, which overflowed, and keys at slot 2, we would still have to iterate through almost half the array to actually find a slot to be able to insert a key at slot 1. So typically, for that reason, the load factor in linear probing maps is kept a little bit lower. Now let's take a look at probe depth. So what I mean by probe depth is, if I wanted to find, or if I wanted to insert an item, what is the length of the chain that I may have to go through? And in this case, all the slots over here have just a 1 probe depth, except for slot 0. So for Kate and all the empty slots, it will just take visiting 1 slot to be able to determine if the key is present, or if we need to do an insert or a replacement of the value there, rather. In the case of the first slot, we have a probe depth of 3. Now, if we look at the linear probing map, it's a little bit of a different story, because unlike in separate chaining, where the probe depth is really localized to the specific slot you're worried about, you can have this problem in linear probing where having a neighboring slot that has overflown by a bit can actually mean that you have worse performance when trying to perform operations on adjacent slots. Now, an optimization that you can do, it's not common, is that you can limit the maximum probe depth of your map. So you can say, if I get to a probe depth of 4, then I will just force a resize of the array. And this will limit the worst case lookup time of a particular key, but at the cost of memory. You'll be resizing more often, because you may have other parts of the array that is completely empty, but yet you end up resizing just because one particular slot has reached the probe depth. So it's not typically done. And if you do it, I suggest really understanding your use cases first. Okay, so let's move on to discussing resizing. This is also a potential operation that you can encounter while you're inserting. So again, if you hit the resize limits, then you may have to do a resize in the middle of your insert. And this can potentially be an expensive operation. And the reason why this can potentially be expensive is because you have to hash every single key all over again. The reason being is that in this particular example, as I mentioned, even though James, Rich, and Jen have completely different hash codes from each other, the only reason they ended up in the same slot in the first place is because the array size, which is what we modulate the hash code by to determine the slot. So if we double the array size, any lookup for Rich may end up starting at a completely different slot. And so we do need to rehash and reinsert every entry back into the hash map once we increase the size of the array. Now, one of the reasons that could be quite expensive is that the hash code method belongs to the key. So the implementer of the map has no idea how complex the hash code function could be. And if you remember the previous example with strings, if you have a very long string as your key, well, the hash code is going to have to visit every single character within that string to work out the overall hash code. As an aside note, in string, that's the reason why the hash code is cached internally inside the string after it's calculated the first time. But nonetheless, it could be, you can imagine with an arbitrary key that you produce to the hash code could be quite complicated to recompute. So one of the ways that we can improve on that, and this is an optimization that is done within the standard library Java hash map, is that we will, inside the node, also store the hash code of the key. So when we insert the key for the first time, we will have calculated the hash code already to figure out where to insert that key. And so we can simply just store that inside the node object. And that way, if we do need to do a resize, the operation is, the expense is mostly down to having to do the memory copies rather than having to recalculate the hash code. So that's quite a nifty optimization. It's also worth bearing in mind that you probably won't have to resize the separate chaining map as much as you will the linear probing map. As mentioned, the load factor in a separate chaining map is typically higher, so we'll tolerate a higher level of occupancy before needing to resize. Since we obviously it's 75 rather than the 50 in the case of the linear probing map. So let's take a look at resizing a linear probing map though. And no such luck with the hash code since we don't actually have a node object to store it in. We could create a third array here and store the hash code in there, but typically that's not done. It's just not really, I mean, often it's a sort of a trade-off as to whether you want to pay the memory cost of the third array, and also the fact that if you are resizing, then you're going to be jumping back and forth between the key slot, the key array, the value array, and the hash code array, which may offset any benefit you get from caching the hash code. But it's worth noting as well that actually if you are, a lot of uses of linear probing maps is for primitive keys. And often if you look up open source libraries for linear probing maps, you will often see code-generated specializations for maps where the keys are, for example, integers. And the reason there is that if you have a specialization of it that is specific for integers, then your keys are stored in an integer array. And in Java, if you're storing an object in an array, you're actually storing a reference to the object in the array. So you have some indirection, but actually in the case of a primitive like an int array, you're going to be storing your values in line. So actually, if you do have a primitive array of keys, then calculating the hash code and calculating the new position and doing the copies is actually quite cheap, since the hash code of a primitive is either going to be itself in the case of an integer, or in the case of other data types like double, there are optimized functions in the standard library that allow you to get a hash code out of them. So it's worth bearing in mind. Again, this is another reminder that knowing your particular use case can help you pick a much more optimal implementation of a map. Now, moving on to the next point, equality. So this is a kind of a similar deal to the hash code problem in that equality can also be quite expensive. Again, if you can imagine your key has a series of, as an object graph below it, and that object graph may be required to be visited in order to do an equality operation between two arbitrary key objects. But unlike hash code, there's no way to cache a value that tells us that, if something is equal to anything else. That's simply not how it works. So equality can be quite expensive when iterating through a separate chaining map. Luckily, there is an optimization we can do, and in fact, the Java standard library also does this optimization, which is that because we have stored the cached hash code, if we are doing an insert and need to iterate, say, for example, into slot 0, and we need to iterate all the way to the end to do our insert, we also need to potentially check if the key already exists in the map. And if it does, then we need to swap out the value. So if we were doing an iteration through here, we would have to do an equality operation through each of these guys. But the nifty optimization of checking the hash code of the thing we're looking up versus the keys that are in the data structure means that we can discount a lot of negatives straight off the bat. And the reason that works is that if the key in the map has a different hash code to the key you are trying to insert, then it's simply not possible that those two keys are equal, just because of the relationship between the equals function and the hash code function. Now, the interesting, I mean, what you can also do, which is an interesting optimization, is along the same lines, is that you can compare the identity of keys as well. So if the hash code does match and the keys are identical, then you know that the key is a match. And this, again, is a very cheap operation to check reference equality. And that should, in a lot of cases, remove a lot of the calls to equals, which is quite nice. And then in the scenario where two hash codes are the same, but the keys are not equal, then we can fall back to doing the equals operation. Now, in the case of the linear probing map, again, we don't have a cached hash code, but we can use the reference equality. And more so, again, if you're using a primitive optimized version of a hash map, then you're going to actually get quite a cheap equals anyway. So it's probably not too much of a concern in that particular scenario. So moving on to iteration. So iteration, again, is something we've touched on. Iteration through a separate chaining map, in this case, is a bit like iterating through a linked list. So we do have to do a bit of indirection, since when we go to an array slot, that's just going to have a reference to the node object. Once we get to the node object, that itself is going to have a reference to the key, a reference to the value, and a reference to the next node in the chain. So we could end up doing a lot of chasing through pointers to actually do our iteration of it. So that could potentially be quite expensive if indeed you care about this cost. And in the case of the linear probing map, again, it's a bit like the comparison between a linked list and separate chaining and an array in linear probing, in that we will probably still have to do, every array slot will hold a reference to the particular key, and every array slot in the values array will hold a reference to the value. But again, this is going to be one less one less bit of indirection that we're going to have to do. And indeed, as I mentioned earlier, if you're using one of the primitive specialized versions of a linear probing map, which are widely available, then your primitive values will be stored inline in the array. So there won't be any need to do any kind of pointer chasing in this particular scenario. Now, if we move on to a final point I want to make about iteration, is that in linear probing, whilst it can be quite cheap to iterate through an array, we are probably going to end up doing a lot more iteration in here, simply because we are storing all of the overflows of hash collisions in the same array. So, and for the same reason I mentioned that we would typically be using a lower load factor. Now, over here, I've colored in the distance that every key is from its ideal slot. And as you can see, James and Kate are in an optimal position over here, in that they're in the exact slots that they would ideally be at. So if we were doing a lookup, we would find them right away. Whereas Rich is one distance away, and Jen is 3 away. And you can imagine if we were to add another key in here, ignoring the resize of the load factor over here for a moment, we can see that actually we'd have to iterate through quite a bit of the array to find Fred, who would normally be at slot 0 if it was empty. But unfortunately is 4 slots away. And we can mitigate some of these problems by choosing a different addressing strategy. Now, linear probing is an implementation of a wider concept called open addressing, which is more used to describe the idea of storing overflows in the array, rather than the idea of linearly scanning if a slot we want to use is occupied. There is an alternative to linear probing, which is called quadratic probing. And it's kind of a similar idea, in that if we want to insert, say, for example, Fred in this particular array structure, what we will do is we will look at slot 0. And if slot 0 is occupied, then like linear probing, we will iterate 1 to the right. And we find that this slot is still occupied. But instead of iterating 1 to the right now, we iterate 2 to the right. And if that slot is also occupied, then we iterate 4 to the right. So we quadratically increase the steps which we take to probe, and that's quadratic probing. And if I had reinserted all these keys using quadratic probing, actually it would end up looking like this, which, as you can see, has actually reduced the worst case scenario in this instance, since if we look over here, we have Fred with a distance of 3 and Jen with a distance of 2, because it's 2 quadratic steps. Now, if we look back and compare that over here, so instead of 2 and 3, we have 3 and 4 here, we can see that in this scenario, quadratic probing will have actually given us an improvement. Though it's worth noting that we will be distributing keys further along inside our array. So if our array is particularly large, then it could be that maybe whilst before our array could have fit into a single cache line for our iteration, we may actually end up doing a bit more work, but that's a more complicated topic that I'll probably not go into too much detail now about. But there is a more interesting strategy as well that's had a lot more attention recently, which is called Robin Hood hashing, which is slightly more interesting than, which is a little bit more complicated than linear probing or quadratic probing. And that's where we apply a different mechanism of conflict resolution. So same as before, if the map is empty when we want to insert, we can simply insert our key into the correct slot. So in this case, much like in the prior example, James and Kate will go into slots 0 and 1 respectively, since those slots are empty. Now, when we want to insert Rich, we're going to get our first collision, which is at slot 0. Now, prior, with linear probing, we would simply iterate to the right until we find an empty slot. In the case of Robin Hood hashing, we actually take a slightly more clever approach, which is that if a slot we want to insert to is occupied, we actually do a comparison between the distance the key in the current slot is away from its ideal position, and we compare that with the key we're trying to insert and its distance away from its ideal position. And whichever one has the greater distance, we put that one in and we swap the other one out and iterate to the right and keep repeating that process. Now that sounds a little bit complicated, but I've got a little example over here for you to look at. So in this case, Rich, we're going to try and insert into slot 0. However, it's already occupied. Now James is 0 away from his ideal slot. And if Rich was to go in here, he would also be 0 away from his ideal slot. So they have the same distance. So we don't do anything, we iterate to the right. And we insert and we find a null slot here. So we insert Rich over here. Now, when we go to insert Jen over here, Jen is going to have the same thing where both her and James will have a distance of 0 at this point. If we iterate one to the right, both Rich and Jen will have the same distance as well. But when we iterate to Kate, we will see that Kate has a distance of 0, whereas Jen will have a distance of 2. So Jen has a higher score, so we will swap them round. And then we iterate to the right, trying to insert Kate. And Kate goes to the next empty slot. And likewise with Fred, it's the same deal again. Since all of these first 3 items have the same slot number, they will have the same score, but Kate only has a score of 1, whereas by the time Fred comes to here, he will actually have a score of 3. So we'll swap them around and insert one to the right. And that is an interesting optimization. And you'll notice that we've actually reduced the worst case scenario overall, but we have to do a bit of extra bookkeeping when doing inserts. So it's important to, again, remember your use case. If you're trying to reduce the worst case lookup time, then this might be quite a nifty optimization for you. But if that's not really your interest, then this is just extra bookkeeping for no benefit. Again, it's a game of trade-offs. So the last thing I want to look at is removals. Now, in the case of separate chaining, it's actually quite simple to do a removal. We actually can remove a key in the same way we can remove a key from a linked list. So if we want to remove Rich in this case, then we simply take the node for James and we detach it from the node for Rich, and we instead link it to Jen. So we can pop Rich out of there. And likewise, if we wanted to remove Kate, for example, we can just remove the node from there, and that's it completed. In separate chaining, in linear probing, it is a little bit more complicated, since if we look at the way that these keys are laid out over here, we have slot 0, slot 0, slot 2, slot 0, because the overflows are sort of mixed together from the different slots. And if we were to remove Rich just by nulling him out, then if we then decided to do a lookup for Jen, then if we took Jen's hash code modulated by the length of the array, that would give us slot 0. We would start slot 0. Slot 0 doesn't have Jen in. We iterate 1 to the right, and there's a null there, so we would stop searching. So that would break our linear probing algorithm. So what we instead need to do is we need to iterate to the right until we hit a null slot and move items that could be moved closer to their ideal slot in that direction by a sort of a compacting mechanism. So once we compact, then the algorithm should work again. Now, that is, again, a bit of extra bookkeeping. There is an alternative strategy, and that is if we want to remove rich, well, then we remove rich, but we instead insert a tombstone, which is effectively a sentinel value into the slot that's been vacated. And the idea here is that if we have a tombstone here, when we want to do a lookup for Jen, we won't find a null slot, so we won't stop searching. We will keep iterating through. And another optimization we can do on top of this is that if we need to do an insert to slot 0 later, we can actually look for a null slot or a tombstone. And in this case, we will simply find the tombstone at slot 1, and then we can use that for another key we insert. But again, it really depends on what your use case is. You know, are you doing a lot of inserts and removals? Are you doing lots of finds and few removals? And that can kind of affect what mechanism you would probably prefer. So in summary, the sort of key lessons to take away, apart from a bit of interesting stuff about some cool algorithms, is that you should definitely know your use case before you decide selecting the particular implementation that you want to go for. The other thing I'd recommend is, again, a lot of off-the-shelf open source libraries have optimizations for primitive keys, which can be orders of magnitude faster than simply using the generic alternatives. So I definitely recommend thinking about your particular your key type. And it would also be worth recommending that you check your performance requirements. Obviously, if you decide to implement something complicated like a compacting key strategy and also Robin Hood addressing, but really there's no performance requirements for you, then it's just a lot of extra complexity that isn't going to provide any benefit. The memory requirements are an interesting one. Again, if you're working on something like embedded, perhaps choosing the linear probing implementation where you don't have to worry about nodes, but also going for a higher load factor may be beneficial to you. Even though you're going to get more collisions, you'll end up using more of the space in your array before resizing. So memory requirements are also interesting to think about. And also, of course, understanding the options that are on the table in the first place before making a decision. That's, and here is a list of some open source libraries that you can use if you'd like to explore further. It's not on here as well, but I definitely recommend reading through the standard library Java hash map, as that again is a very interesting implementation of a hash map. And that's the end of my talk. And if you have any questions, I'd really happy to see if I can give a shot at answering some of them. Thank you. Let me see if I can find the... does anyone have any questions? Nope. All right, nothing in the chat window? Cool. Thank you very much. Right, cool. So that's the end of my presentation. The next speaker is going to be Lakshmi, and she's going to be talking about domain-driven design.
You can see my screen?
Yep.
Okay, cool. Thanks, Sam. Thank you everyone for joining. Yeah, especially when the weather is so good outside. Really appreciate you taking time to join us. So today I'll be talking about domain-driven design. A bit of background about myself. I'm Lakshmi. I work as a senior engineer at Tesco. So what I would like to tell you about in the next half an hour or so is basically why you should use DDD, what is DDD, and then some of the strategic and tactical patterns which are available in DDD, which will help you do DDD better. So basically domain-driven design is a philosophy in itself. So in half an hour, I'll try to just give you a very high level bird's eye view of DDD. So the obligatory, what is DDD side? So domain-driven design was a concept coined by Eric Evans in 2003. So he wrote the book with the same name, Domain-Driven Design, Tackling Complexity in the Heart of Software. As you can see, it's domain, your design is driven by the domain. So the focus should always be on the domain and not on the technology. That is the key concept of domain-driven design. And also it stresses the importance of the communication between, the domain experts and the technical experts. So you might be thinking, why did I select this topic? It's like a concept coined in 2003, right? I was wondering the same. Should I be talking about this? Like, for example, Barry here or Steve Poole said, Lakshmi, just talk about anything you're passionate about. Don't worry whether it's flashy new tech. It need not be flashy new tech always. But then I started thinking, okay, I am passionate about DDD. I've used it in a personal project, so I could, relate it much better. But then I started exploring, what is DDD now compared to in 2003. And what I discovered was that there is a continuous and renewed interest of DDD. People are embracing DDD in better ways to understand the domain better. So if you focus on the key technology trends which are happening at the moment, we are all moving towards serverless, and we want our applications to be deployed on AWS, Azure, basically on the cloud. So the future is less infrastructure, and we are trying to focus more on the application. So unless you are hardcore Kubernetes or infrastructure developer, as application developers want to spend more time on the domain rather than trying to debug why my Elasticsearch is not scaling or why my MongoDB is not deploying. So we want to offload the infrastructure as much as possible. And also we want to write software which is more evolving and sustainable. So by that I mean, for example, it's not like just writing some lines of code and throwing it out for the release. And then when the next feature comes in, you really struggle to maintain that. So that is not we want to do. We want to write something which is evolving and which is more sustainable. But to do that, we need to understand the problem. So the problem is we don't understand the problem. Like we don't understand the domain. As developers, we are very excited to code, but we don't spend enough time understanding what needs to be done. And I can bet that, you can't write a simple solution to a problem unless you know the problem. You could, use solid principles, dry principles, write a bunch of test suites, try to, use as much abstraction as possible, try to write the best software. But if it doesn't solve the problem, then what is the use? So our main idea is to, write simple solutions to a problem. DDD provides some tools to do that. There are categorized into two basically. Some are strategic and some are tactical. So the strategic tools are basically around understanding your domain. Like you have concepts like bounded context, ubiquitous language, big ball of mud, core domain, subdomains. And the tactical patterns mainly relate to the implementation. So now that you have the domain, how do you write a domain-rich model using value objects, aggregates, and stuff like that? So today I'll be focusing more on the strategic side of things. So let's start with modeling our domain. You get a new project, you get a new story, and we are excited. Okay, let's do this. So we want to keep it as clean as possible, as simple as possible. So when you start writing your first project, or when you start from scratch, it's always nice and clean. So you have a customer object in this example and a couple of other classes which are more related. So you follow the single responsibility principle and write really neat code. Then you get some more requirements, for example, add the product details to this order and stuff like that. So it grows a little bit more. Then you get some more requirements, you start adding more classes, and it grows a little bit more. And eventually, this is what you end up with. So a lot of intertangled classes, lot of dependency, you don't know what is happening where. And that is what is called as the big ball of mud. So big ball of mud, what Eric Evans says is that, basically, it is doing something, but nobody knows how it is doing it. So it's like a spaghetti code compared to a layered bowl of lasagna. Imagine you have a bowl of spaghetti. So it's all intertangled code and you don't know what is happening where. And if you try to, implement something, you'll end up breaking 10 things. So big ball of mud is definitely something we cannot be proud of and we need to avoid. But when you start developing, it's very easy to get into big ball of mud because your domain grows, your business grows, and you start adding more classes to your domain. So the creator of Erlang, Joe Armstrong, put it nicely to this name given to, for example, what you call that big ball of mud. So basically, when you look for a banana inside a big ball of mud, you get a gorilla holding the banana. So you get the full thing, right? Maybe even the jungle. So he used this to describe object-oriented design basically, but then it completely applies to this big ball of mud where you have a lot of classes. So how do we overcome this problem? I'll give you a moment to read the play of words there. So basically, context is the king in DDD. So you can mean the same word could mean different things in different contexts. So when I say a mouse, is this my computer mouse or the mouse? So you don't know what it is until you get the context. So the focus on DDD should be to understand the context. And that is what is called as a bounded context. So basically, you put a boundary around your context and everything in that context should make complete sense to you. If it doesn't make sense, then probably it shouldn't be in your context. So everything in the context should have explicit meaning. Let's take the simple example here where you have a product, then you have the reviews where you have reviews about the product, the pricing domain where you have the price, and catalog where you have a bunch of description, image, some other properties related to the product. So imagine if you create a big product, God class having all these information. So eventually you will be leading towards big ball of mud. So basically the idea of bounded context is just focus on one thing. So if you're on the pricing domain, just focus on the price. You shouldn't be pulling in information about the stock into your price or maybe not the catalog into your price. So that is the meaning of bounded context. So bounded context is the central to domain-driven design. So you decide what nodes to go inside the context and also to check out anything which is outside the context. And when you start writing domain models, it's very easy to do anemic domain models. This was the concept coined by Martin Fowler. Like, especially if you are from a Hibernate background, you just create classes with a bunch of getters and setters, and your domain model is just a replica of your database. And that is where, the anemic domain model comes in. So you then write customer helper, customer manager, customer service to do all the business logic, and your actual domain, which should have the business logic, will have a bunch of getters and setters. So, you can imagine the problem with that type of model, right? It has low cohesion, then your business logic is scattered everywhere. It is hard to change something, so there is no consistency. So that is something we need to avoid. And we should concentrate more on, creating rich domain models. So in the rich domain model, your data and behavior sits together. You try to, put all the business logic related to the domain inside that domain model, and you shouldn't scatter it everywhere by creating other classes. So domain model are just ordinary classes, but they focus mainly on the business instead of the infrastructure. I would like to quote this from Eric Evans. So initial models which we create are usually naive and superficial, because when you create the models initially, even the domain experts might not be, knowing everything about the domain. Even you are new, you might be not knowing the domain, but you should just make a best effort to understand the domain and then you refactor. So I have come across this myself so many times that, I write code which might not actually fit into the domain model. But then when I refactor, I understand more about the domain. So refactoring, don't think refactoring is just, cleaning your code or upgrading Java or getting rid of a bunch of unused classes. It is more about simplifying your domain by using more, insights of your domain. So the more you know about the domain, the simpler you can make it. That is refactoring. And DDD doesn't focus anything on the architecture, but then this hexagonal architecture or the onion architecture, or it's also called as the port and adapter architecture, is something which is really useful. So basically here you have the domain model at the center. It shouldn't have anything about the infrastructure. And then you write a bunch of application services which actually communicate to your user interface or to your infrastructure. Okay, so the next important concept in domain-driven design is ubiquitous language. So if you look up the dictionary meaning of ubiquitous, it means everywhere. So what is ubiquitous language? It's like a complex term for a very simple, logic. When you communicate with domain experts, we always fracture the language because we speak something, we as technical experts or developers, we try to put lot of technical jargons whenever we speak to the domain expert. So one of our product managers even said, yeah, half of the time I don't understand what you guys speak because you introduce lot of technical jargons into your, while speaking, and it's very difficult for me to follow you. And I'm sure most of you might have seen this image where the customer wanted a tired swing, but then he explained it as a 3-tiered swing, and the business analyst thought, oh, he wanted a sofa with a swing, and finally the developer implemented it in some other way. So this is the fractured language problem, where if you don't understand your customer needs properly, you end up creating different things. How do we overcome that problem? We overcome by using ubiquitous language. So when you are in a room with everybody, then you should speak in a language that is everybody understands. So that is ubiquitous language. There should be no technical jargons. At the same time, it should be very explicit. For example, it is the same at the other end as well, right? So the domain experts might struggle to communicate to us. So the idea of ubiquitous language is to make the communication smooth across both the parties. I just found this very good example on the internet, which I could relate to myself. So let's just read this. For example, your product owner comes to you and says, I want to add a coupon box to the checkout flow. So as a developer, you start thinking, okay, I'll add a coupon route to the checkout API, and we could post it and then create a coupon object in the backend. Then your teammate jumps in and says, wait, we don't call them coupons, we call them discounts in the backend. And the checkout API is technically implemented by the right commerce API. Oh, right. Then you say, okay, let's create a coupon route, and it creates a discount object, and we need to remember to call the right commerce service and not the checkout service. So you can see I've highlighted in red the problem with this. So what is wrong here? So we are talking about the checkout flow, but the right commerce API is implementing it, and the product owner is saying coupon, and in our code it is discount. So then we write extra documentation to say it's coupon and not discount. And if somebody new comes to the project, they might end up creating new classes, and they might introduce more bugs because it's so hard to understand what's going on there. So the idea of ubiquitous language is to create a language which is like your backbone for the application. If you say something like, if it is replaced, if you say coupon and then next day it is replaced with voucher, it should be replaced everywhere. When you talk, in your conversation, in your code, in your testing, in your documentation. And if something changes, it should be changed everywhere. So that is the idea of ubiquitous language. So having a living document like a glossary where everything is explicit and you specify it and you keep updating it. So the last topic I wanted to cover was, now we know that the domain is important. We know we should use a language which is understood by everybody. But then how do we understand this domain, the domain discovery part? So to be honest, as developers, we are not great communicators. Either we start speaking a lot of technical stuff or we don't speak at all. We tend to assume a lot of things that this is how it works. So when a product owner comes to you for a story, you just say, okay, I've understood everything. Bye, I'll take care of it. You don't worry. That is how the usual conversation is, right? Because we avoid discovery because discovery is not something very easy. Domain-driven design says you need to understand your domain, but it doesn't provide any good tools to discover your domain. And over the years, people are coming up with different technology or different ideas to understand the domain better. So for example, imagine showing a bunch of UML diagrams to your business experts. So they might understand, but they would really struggle hard, right? And then try bringing up everybody in the same room, all like your testers, your developers, your domain experts. That meeting would definitely be very boring because we don't understand each other. And then this guy comes, Alberto Brandolini. He is in fact called as the savior of DDD because he introduced a simple concept called event storming. So event storming is a very simple concept where you don't bring in any technology to the room, but everybody gathers in the same room. People across the board, your experts, your product owners, developers, testers, whoever is involved in that project. Then you take a bunch of sticky notes and then you implement an event in your domain end to end. So that people try to, it's like brainstorming, right? So instead of brainstorming, you're storming an event in your model. So it's a very simple concept, but a very powerful one. So finally, like I would like to add that, although domain-driven design is a very popular concept, a philosophy, it's not the silver bullet for everything. So domain-driven design needs to be used when your domain is complex enough and it, needs something which is like this so that you understand it better. But maybe if you're developing a CRUD application, then, it might not be sensible to go with the DDD route because you'll be overcomplicating it. At the same time, if you have to, do a very technically complicated solution, but the domain is not that hard, then in that case also DDD might not make sense. So DDD makes sense when your domain is complicated enough. So finally, to reiterate, what are the do's of DDD? Speak to your domain experts, respect the ubiquitous language, find your core domain, and don't expect to find all the knowledge at once. So keep iterating and refactor towards deeper insight. At the same time, when you talk to your domain experts, don't concentrate on technicalities, don't expect the ideal model, don't over-engineer, and respect your context boundaries. So I would like to just refer you to some of the important books of domain-driven design. Obviously, the blue book is the important book from Eric Evans, but I would like to mention this book as well from Von Vernon. So this is usually called the red book, which is a bit simplified version compared to Eric Evans' book, because Eric Evans' book is really hard to comprehend, especially if you're trying to read for the first time. But the book I really liked was Patterns, Principles, and Practices from Nick Tune. You have to hear Nick Tune speak because, you can relate to so many things which he speaks, and it is more related to the current technology trend as well. So I really liked his speech. And yeah, unfortunately, I couldn't show much code because I wanted to focus more on the strategic patterns, but maybe on the tactical patterns, we could show about value objects, entities, and stuff like that. But there is this IDD sample from Von Vernon on GitHub if you want to explore to see how the DDD code looks. Finally, I would just like to end with a quote from Alberto Brandolini. So it is not the domain expert's knowledge that goes into production. It is the assumption of the developers that goes into production. So whatever we assume is production, right? So let's hope we assume what we do correctly with DDD. Thank you. Thanks for listening to me.
It's really interesting, Lakshmi. There are a couple of questions popping up on the chat group.
Okay.
From Lewis, Lewis is asking, do you only implement validations in domain layer? So the request DTO passes through the controller, passes through the application services, passes through the domain services without any validation?
No, you should implement the validation in your model, right? So for example, if you say, if your customer is like, has a name of this length, or if your customer ID should be this thing, then you put that validation in the customer object. But for example, if there are few things which make sense to put it on the UI layer, or if you think it doesn't naturally fit into the domain, then that is something you need to put it inside the service layer. That's why you create a service layer when you think that, you can't put that, that doesn't naturally fit into the domain. And also maybe you need to call the database to do the validation. In that case, you can create a service. But if the business logic naturally fits into the domain, then you have to put it in the domain.
Okay, cool. And there's another question from Hemant, who's asking, how would we migrate from an existing design to a domain-driven model? Would event storming be a good start?
That is a very good question, actually. Yes. So basically, recently we migrated an existing project into, using some of the concepts of domain-driven design, especially using bounded context, so that we separate out the code because it was a big ball of mud. So yes, event storming is definitely a good idea, especially in this case, because you know the domain already and you're trying to refactor. So bringing in everybody in the same room and trying to event storm will help you, understand your domain better and also get new insights into the domain so that your refactoring will be better.
Okay, cool. And a question from Jeremy. What are some examples of domain discovery that developers don't like to implement?
I would say it's mainly talking to the domain experts because, sometimes we think we don't want to use their time because we know everything, or sometimes we are hesitant to ask because they might think we are stupid or silly that, if somebody says an app driver or an app, who is that app driver? Is it actually the Uber driver who is using it, or whether it's the customer? So if you just say app user, then who is that app user? So I think, yeah, that is something as developer we hesitate to ask because we think it would be silly to ask, and we kind of assume things. So yeah, that is the hard part of domain discovery, I guess.
Yeah, I completely agree with that one. Lewis has another follow-up question. What are the typical operations handled by an application service? What are the differences with a facade?
That's a good question, actually. Application service, we could consider it as a facade. So basically, for example, if you have a REST API, then your REST API needs to call your repository, right? Or your application service needs to call your other services to get the data. So that is where you use the application service. It is a facade, basically. So where it is an entry point to your REST API or your event system. So it's basically an entry point into your application, and then you decide the flow from there.
Okay, and last question, actually, this one's my one, actually. I really enjoyed the talk, and I really like the idea of using ubiquitous language, and I try and use that on a day-to-day basis. The difficulty I find is with, obviously you have different languages for different context mappings, and if you're creating a glossary on some kind of wiki, often I find it either goes out of date, or people don't, look for regular updates in it, because obviously keeping anything separate to your code is likely to fall by the wayside when it comes to development. Is there any techniques or mechanisms that you've tried that you've had some success with documenting what the glossary is, or is a wiki really the only way of going about it?
Yeah, I can definitely relate to that, because it usually happens, right? We initially start with, we are excited and we write the wiki, we write the glossary, but then it's very hard to keep it up to date. At least from my suggestion is, use your code as your glossary. So basically when you write your BDD tests, make sure that you use the terms which are your glossary, so that even if your domain experts read it, they should be able to comprehend it. So rather than having the wiki, maybe your code should be the wiki.
True, I agree. But like the use of the terms is obviously guaranteed by writing stuff in code. It's more like, when, say for example, you have some ID that, one example would be like a customer ID, and actually understanding what the meaning and the use of the context of the customer ID is very difficult to understand without examining all the code points to understand how it's used. So like what is the definition of the customer ID? What is the life cycle of the customer ID? And that kind of stuff becomes more difficult to discern just from reading code. I was wondering if you had a way of like any technique for actually where you define what the term is rather than just seeing it in the use case.
I agree. I mean, it's not an easy thing to do, but one thing which I was reading even in the domain-driven design is that basically you should name your, classes or domain objects in such a way that it should tell you the meaning. So rather than having to, map from one thing to other. So customer ID in this case is straightforward, right? It's the ID of the customer. But maybe for complicated domains, it's a bit difficult. I can understand, but as far as, possible, we need to name it and try to overcome that problem.
Thank you very much. I think that's the end of the questions.
Thank you. Yeah, that's it. I think. Thank you so much for joining. I really enjoyed. Thank you.
Yeah, thank you very much to both the speakers. I think Barry mentioned at the start that this was the first time either of you folks did a full talk. And to be honest, if you hadn't said that, I wouldn't have known. Like, I would definitely see a talk by either of you again. So yeah, please do some more.
Thank you very much.
Thank you.
Yeah, and thanks everyone for coming.